Conductance.
In Canvas, we are just have
Recording. Okay, conductance. So that is the topic we are going to discuss today. Now, what is conductance? Specific conductance, molar conductance, equivalent conductance, these are the topic of discussion. Now, let's start from the beginning. Conductance of electrolytic solution. Now, what is electrolyte? Electrolyte means any solution that can carry electricity and produce some new material. Like acidified water, if you do the electrolysis, you get hydrogen at the cathode and chlorine at the anode. Hydrogen at the cathode and chlorine at the anode. If you take sodium chloride, do the electrolysis, what do you get? Aqueous solution of sodium chloride electrolysis, if you perform, what will be the product? No. Aqueous solution I told. So you will get hydrogen at the cathode and chlorine at the anode. Because sodium ion is not getting discharged. Sodium ion is in the electrochemical series much above hydrogen. So H plus will be discharged and you will get hydrogen as the product, not sodium. If you take molten sodium chloride, do the electrolysis, then only you get sodium. Please stop talking, all of you. So if you take molten sodium chloride, do the electrolysis, you get sodium and chlorine. If you take aqueous solution, you get hydrogen and chlorine. And if you take dilute solution, then hydrogen and oxygen, not even chlorine. Because OH minus and Cl minus in the electrochemical series, they are very closely spaced. So which one will discharge depends on concentration. In that case, it will depend on concentration. If you have a chloride ion and hydroxyl ion as the competitor at the same place, so then which one will discharge first? That depends on the concentration. If it is diluted, then OH minus is larger in concentration. That's why OH minus will be discharged and you get as a product oxygen. But if you have concentrated NaCl solution, aqueous solution, then you get chlorine. Okay. But regarding cathodic product reduction, there obviously hydrogen will be discharged, never sodium. But you can change the scenario. Instead of taking any other electrode, if you take mercury as the electrode, then sodium may be discharged. Because sodium has a very strong affinity towards mercury. It will give you that amalgam. Sodium amalgam. Because sodium will be discharged in presence of mercury and dissolve in the mercury itself, producing sodium amalgam. If you have any talking, please go out, do your talking and then come back. Okay, so this is electrolytic solution, regarding electrolytic solution electrolysis. Now, there are some solutions which are not called non-electrolyte. For example, kerosene, benzene, these type of things, if you do the electrolysis, it will not happen because there is no ion present at all. Benzene, kerosene, any type of sugar solution, you cannot do the electrolysis because these are non-conducting. So, no conductors, and there are some conducting material electrolyte also can be divided into two categories. One is called strong electrolyte, other one is called weak electrolyte. Strong electrolytes are highly dissociated in the aqueous solution. Automatically, you get more than 80%, 90% dissociation. And some electrolytes are called weak electrolyte, which are dissociated hardly 20%, 30%, not more than that. Okay, so those who are highly ionized, strong electrolytes, they are usually found mineral acids, mineral alkalis, they are strong electrolytes like NaOH, HCl, H2SO4, HNO3. These are the compounds, all are strong electrolytes. Some chemicals like acetic acid, citric acid, which are organic acids, weak electrolyte, because they are dissociated little in the aqueous solution. Okay, so those who are dissociated little, they are called weak electrolytes. Those who are dissociated very strongly, they are called strong electrolytes. Okay, so this is the your conductance of electrolytic solution. That is the first point. Now coming to the second point, specific conductance. What is specific conductance? Specific conductance is the conductance of 1 cc of an electrolyte. 1 ml, 1 cc. Do you know the difference between ml and cc? There is a slight difference, very close. Okay, ml and cc not exactly same. ml means milliliter and cc is cubic centimeter, but cubic centimeter and your milliliter, there is a relationship. Okay, it is 1.002 something like that. There is a relationship, not exactly same, slight difference is there. Anyway, but normally in all practical cases, milliliter and cc, we are taking same way. Okay. So now specific conductance is conductance of 1 cc of an electrolyte. That is the difference. So another way you can explain, we have two electrode, area of each electrode is 1 square centimeter, and in between the distance you keep 1 centimeter. The gap is 1 centimeter and the area of cross section of each electrode is 1 square centimeter. Then how much solution will contain in between? If you have two electrodes, each one, cathode and anode, both are 1 square centimeter area, and in between the electrode you have 1 centimeter gap, then how much solution will be contained in between? 1 cc. So that is the conductance of specific conductance of 1 cc of electrolyte. That means we can explain this way. Either we can say it is the conductance of 1 cc of electrolyte, or otherwise we can say when two electrodes placed 1 centimeter square area electrodes placed in between, the gap is kept 1 centimeter, the solution contained in that, the conductance of that solution inside this electrode will be called specific conductance. Actually they are same, no? They are same. Whatever way we explain, it is the same thing. So this is specific conductance of 1 cc of an electrolyte. Okay. Then equivalent conductance. What is equivalent conductance? It is the conductance of one equivalent of an electrolyte. Specific conductance for 1 cc, equivalent conductance for 1 mole. Now, equivalent conductance for conductance of one equivalent amount of an electrolyte. One equivalent amount of an electrolyte. Now, what is the volume of one equivalent electrolyte? That depends on concentration. What is the volume of one equivalent amount of an electrolyte? That depends on concentration. How? Achha, what is the equivalence rate of sodium hydroxide? Any idea? What is the equivalence weight of sodium hydroxide? Equivalent weight of sodium hydroxide. Any which? কত হবে? No idea. Molecular weight is 40. Okay, molecular weight is 40. I'm telling you. Then what will be the equivalent weight? Bivalency. What is the valency of sodium hydroxide? It is univalent. So valency is 1. So that's why it will be 40 by 1. That means equivalent weight is also 40. So 40 gram of sodium hydroxide you are taking and dissolving into certain water. Okay? 40 gram of sodium hydroxide, that is one equivalent amount. You are dissolving into some amount of water. That some amount may vary. If you make it very concentrated solution, the conductivity will be more. But if you make a dilute solution, conductivity will be less. But total conductance of one equivalent amount of an electrolyte is equivalent conductance. So equivalent conductance depends on concentration, the molarity. Equivalent conductance depends on the concentration in terms of normality. So what is the relation? Suppose V is the volume of one equivalent amount of an electrolyte. So this V will be equal to your 1000 by N. By definition, 1000 by N. N means normality. Because in the normality, what is the definition of normality? Number of gram equivalent dissolved per liter. Liter means 1000 cc. Because specific conductance we are talking about 1 cc. So here also we should make it into cc. Otherwise we cannot make a relationship. So our equivalent conductance represented as cap lambda EQ. Cap lambda EQ. That is equal to 1000 by concentration. Now if the concentration is in terms of normality, then because equivalent, so normality concentration, so 1000 by normality concentration. That is the relation. Okay. So specific conductance and equivalent conductance, there is a relationship. Lambda EQ equal to kappa into 1000 by C. Okay. Let me write down. There is some resistance. Length is L. Area of cross section is A. So R equal to rho into L by A. I think these you all of you know. Ohm's law. Okay, you must remember, because in the sometimes in interview also people can ask Ohm's law. So if you don't know Ohm's law, you are automatically discarded. So you have to know this type of small thing. Should not ignore. So 1 by R if you take, that is capital lambda, that is equal to 1 by rho into A by L. So that is equal to kappa into A by L. Therefore, kappa equal to cap lambda into L by A. Got it? From Ohm's law, I am telling you have a length of some wire resistance, that is L. Area of cross section of the wire, the resistance can be wire. So the area of cross section of the wire is A. The resistance of the wire will be R, proportional to L, the length, inversely proportional to the A, the area of cross section. So R equal to rho into L by A. So if you take inverse 1 by R, that is called conductance, because we are discussing conductance. So first you have to know resistance. So 1 by resistance is conductance, and it is applicable for metal, non-metal, everything. Okay, this particular formula or this method. Unit conductance. Conductance of unit of conductance, not unit conductance. Unit of conductance is mho, ohm inverse. Conductance is ohm inverse, and specific conductance ohm inverse centimeter inverse. And you have already done one experiment, that is experiment number 1, conductometric titration. There in the plot you have used the unit ohm inverse centimeter inverse. So, but you have already plotted conductance, not the specific conductance. Then why you are using ohm inverse centimeter inverse? Because our electrode is made in such a way, two cathode and anode, both are 1 square centimeter, and the gap is also 1 centimeter. That means actually you are taking specific conductance, not the conductance. You are measuring specific conductance all the time. Because our electrode is made that way. You cannot do anything else. Electrode is made in such a way that two electrodes are there, cathode and anode, 1 square centimeter area, and gap is. So actually you are measuring specific conductance. That's why your unit, when you plotted, the unit was ohm inverse centimeter inverse versus volume of NMH added, so it was ml. So that's why you always you say that write the scale like this way: 1 SD equal to 0.1 ml x-axis and y-axis, 1 SD equal to 0.1 ohm inverse centimeter inverse. Always we say that to write the scale. Why it is? You have to understand this way. It is actually specific conductance we are measuring. Okay, so here capital lambda, and I have made a relationship. Kappa equal to, what is kappa? 1 by rho. What is rho? Resistance, specific resistance or resistivity. Specific resistance or resistivity is your rho. If you take 1 by rho, that is kappa. That is specific conductance. So specific conductance kappa equal to actually lambda.
1 by R.
1 by R is capital lambda. 1 by R is capital lambda. R is resistance. So 1 by R is conductance. So and rho is specific resistance. If you take 1 by rho, that is kappa, specific conductance. And what is specific conductance? Conductance of one system of an electrolyte, as we told already. So there is specific conductance. Make it specific. That means L equal to 1, A equal to 1. If you make L equal to 1, A equal to 1, then actually what you get? No, here kappa equal to lambda. Kappa equal to lambda. So that is specific conductance. And equivalent conductance also we can make a relationship. Lambda EQ. Lambda EQ, equivalent conductance equal to kappa into V. That is simple relation. Lambda equal to kappa into V. Kappa is specific conductance into V. V is the volume of one equivalent quantity of electrolyte. It is the volume of one equivalent quantity of an electrolyte. Now this volume depends on concentration. If you add more solvent, then volume will be larger. If you add less solvent, volume will be smaller. But this quantity, that means will depend on concentration. So we can replace the V by parameter 1000 by C to make it general. Now this C we can also replace because it is equivalent. So instead of C, I can use the term N. N for normality. Normality concentration. C is a general term. C means concentration. Now if it is a normality concentration, so we can use the term N. So the relationship is cap lambda equivalent equal to kappa into 1000 by N. That is called equivalent conductance. Now molar conductance also will be similar. Very, very similar. What is the difference? It will be lambda M equal to kappa into 1000 by M. Yes, that's it. Okay, very close relation. For lambda EQ equal to kappa into 1000 by N, whereas lambda M equal to kappa into 1000 by capital M. M for molarity. Okay, because as I told C, so C will vary, na? If you take normality concentration, you can take molar concentration. Accordingly, your thing will be, total volume will vary. So it will be 1000 by n or 1000 by n. So another relation is this, capital lambda m is molar equal to kappa into 1000 by n. Then coming to the Kohlrausch's law, but before going to the Kohlrausch's law, another thing to have to clarify, what is infinite dilution? To know the Kohlrausch's law, first you have to understand what is infinite dilution. By the way, if I take some strong electrolyte and dilute it, what will be the difference? It is already highly dissociated, so 80%, 90% dissociation is already there, or maybe almost 100% dissociation is already there. Like sodium chloride, in aqueous solution it will be more than 99% dissociated, almost 100% dissociated. So in that case, if you increase the dilution, that means you add more and more solvent, practically no further dissociation will take place. So is there any difference if you do it dilution, do the dilution? Huh? So it will become more and more diluted, molarity will decrease. But what is the molecular level changes? Is there any changes in the molecular level? What do you think?
So molecular level means
Molecules, is there any change in rearrangement of the molecules? Any modification of the rearrangement of the molecules?
Sir, number of ions per unit area decreases.
Decreases. That is the meaning of dilution. That's true. But along with that, one thing you have to understand, when the molecules are in a cluster form, they have less mobility because they are bound. And when you are diluting this solution, they are going away from each other. So this cluster is already broken and mobility will increase. So they can freely move. That is the main difference coming. Mobility will increase and they can freely move now. Earlier they were in a cluster form, so they could not move freely. Now their degrees of freedom will increase because you are diluting, so they are going away from each other. Molecules are not not controlled by other molecule. There is no influence. They are totally becoming independent. As they are going away from each other, they are totally becoming independent. They are going away from each other. Got it? Got the difference? So that is happening for a strong electrolyte. Because the ionization respect, if you consider the ionization, it is already there. Before dilution, after dilution also, there is not much of ionization difference. So what is the difference then? Mobility. They are earlier in a cluster form, now they are getting separated from each other and they can freely flow, freely move. Okay, that is the difference. Now if you take weak electrolyte, they are very little dissociated, 10%, 15%, 20% dissociated. But if you go for more and more dilution, then ionization will increase, improve the ionization. So it will be 30%, 40%, 50%. Very fast ionization will take place now because molecules are getting separated, and water molecules, if I take solvent water, so the water molecules actually pulling the molecule from both sides, all different directions, and as a result the molecule is broken. So ionization is taking place, and not only that, after the ions are formed and sufficient water molecules surrounding it will dissolve the individual ions. So they are taking care of ion also, so it is getting dissolved and it is giving some sort of energy that is called solvation energy. More the separation, more the number of water molecule, better will be the solvation, is clustering the molecule. Okay, one example I can draw like this. Na plus could you understand now what I'm telling? Water molecules are represented by dipole. These are all water molecules surrounding the sodium ion as a cation and forming a sort of cluster that is releasing some energy. Why energy is released? Because this opposite pole, they are attracting. This is ion dipole interaction. Sort of force there. It is only electrostatic force, some sort of electrostatic force of attraction, and it is called Kizom force. So this ion dipole interaction is giving some stability. So and as a result, it is getting dissolved. But if you take suppose as sodium acetate, So there also sodium gets dissolved like this. Acetate ion is also getting dissolved like this. So water molecule is surrounding all the cations and anions. So small molecule like acid, sodium acetate, or suppose acetic acid. Acetic acid itself, not sodium salt. Acetic acid also gets ionized. Sodium ammonium hydroxide gets ionized because it is diluted. So more ionization. So more ionization is taking place in case of weak electrolyte due to dilution. But strong electrolyte, if you do go for more and more diluted, then they are getting separated and their ionic mobility increases. As a result, there is some outcome. When you dilute more and more and more, something like this will happen. Conductance versus root C. If you plot, you get a plot like this. So this is, you can interpolate. You cannot directly touch, but you can interpolate. Why cannot directly touch? Because here is zero concentration. And zero concentration means simply the solvent itself. So practically it is not possible. That is not your solution. That is solvent only. So that's why you can make it tends to zero, but cannot make it exactly zero. So you can interpolate. You know extrapolation? This is called interpolation. So you can interpolate and you can touch the y-axis. So here you get the maximum dilution, and in maximum dilution condition you can get very high conductance also. High conductance. That is called conductance at infinite dilution. Conductance at infinite dilution. When C tends to 0, conductance is said to be at a maximum position, that is called lambda 0. Okay, that is called infinite dilution situation. So you can call it lambda 0. And this lambda 0 means concentration is concentration tends to 0 and dilution is tends to infinity. And here this particular thing will be valid. Okay, and what is small lambda? Plus, that is the cation and anionic conductance at infinite dilution. So this is called the Cold-House's law. At infinite dilution condition, the conductance of an electrolyte is equal to sum total of individual ion conductance values, cation plus anion. Cation plus anion. Now you can have always not the very simple molecule. It can be a bit, for example, barium chloride. So 1 barium 2 chloride. So 1 cation 2 anion. So that means there will be some coefficient also. So we can put some coefficient over there. Okay. So you can some number of C1, C2, some number of coefficient we can add also. If you have only one cation, one anion, then this is the formula. But if you have multiple cation and anion, accordingly you will have to give the coefficient will be added. Coefficient that can be added. So this formula is called Cold-House's law. Total conductance of the electrolyte at infinite dilution is the sum total of individual ion conductance values. No, actually they are totally getting separated at infinite dilution condition. Totally separated. Cation is not influencing the anion, anion is not influencing the cation. In that condition, the total conductance equal to sum total of cationic conductance plus anionic conductance.
The conductance may be different in case of cation or anion.
Obviously different. I can give some example. No, their movement, speed different. Achha, H plus, to tell you, give your answer, I am giving some data. Get the data, you will understand. I remember this data because H plus and OH minus is most popular, most common. So from the data, what you want to see? One is 348, other one is 198. Whether if you take sodium, it will be around 60. They are not different, obviously different, depending on speed. एक पतला है मोटा है.
Size of.
Simple. Yes, depends on size. If it is very small, it can move faster. If it is a larger, it will be sluggish. It will be slower.
And sir, how it is root C in the graph?
Root C, how? Acha, there is a
From any kind of relation or?
there is a straight line equation actually. See the straight line? This straight line equation, na? So there is a straight line equation. If you take root C, then the straight line equation comes. And if you take C, then equation will be not that straight line. It will be no, not irregular. Like I say, it will be exponential type of plot. So to avoid that, this is taken. Acha, now one thing from the diagram, as you go towards zero, that means dilution is increasing. For strong electrolyte, what you can see that it is linearly increasing. But for weak electrolyte, what you can see, it is exponentially increasing. For strong electrolyte, lower the concentration, your conductance is increasing, but linearly increasing. Whereas if you take weak electrolyte, conductance is increasing exponentially, not linearly. From the diagram you can see, na? It is exponentially increasing. Infinite dilution means when C tends to 0. You have taken one bucket full of water and there you have added 2 drops of HCl. You cannot measure the concentration. Isn't it very highly diluted? It's so diluted that practically concentration is 0. Practically. Because 2 drops of HCl, if you add into one bucket full, you cannot measure the concentration also. But still, it is conducting. Water, if you take, it is not conducting. But if you add 2 drops of HCl, the whole solution will become conducting. So difference is there. Though you can say it is very, very diluted, what is the use? Yes, there is use. You will find it is conducting, otherwise it is non-conducting. A few drops only make it conducting. Okay.
Sir, as you can say that it increases exponentially.
Exponentially is this one. This plot if you follow. Rising very sharp manner.
Achha. And before that,
These are straight lines. This is for strong electrolytes. These are for strong electrolytes, AC, and this is for weak electrolytes.
and the conductance decrease.
Conductance, no, your concentration decreases, the conductance is increasing sharply, and this is due to the mobility only, and this is due to annihilation. Yes, there is a relationship. Lambda equal to lambda 0 minus some constant into root c. Lambda equal to lambda naught. I am writing the equation. Lambda equal to lambda c at a certain constant equal to lambda naught means infinite dilution minus a root c. And that a value depends on particular electrolyte constant. But this equation is applicable only for strong electrolyte. Linear equation, na? It is applicable only for strong electrolyte, not for weak. So to make this simple relationship, root C is plotted. Otherwise, if you plot the C, you get some curvature, but you cannot make a very good relationship so that you can follow, you can find out the values, you can relate the different type of electrolyte solutions. If you find out the A values, so different electrolyte you can make a chart. So that benefit you are getting actually. Substances whose solution in water conducts electric current, that is electrolyte. Conduction takes place by the movement of ions. Substance whose aqueous solution does not conduct electricity called non-electrolyte. This is already I have discussed. So I can go ahead. Types of electrolytes, strong and weak. That also I have discussed before opening the PowerPoint itself. So you can just go through, have a look, so that I can go ahead. So this chapter is actually your thermodynamics as well as electrochemistry. So thermodynamics part I have more or less completed, that's why I have started electrochemistry. Specific conductance also I have discussed. This is the thing. Now, one thing I have not told you, L by A is called cell constant. Be careful, huh? Don't fall down. Achha, kappa equal to L by A to conductance. Now this L by A, this is called cell constant. Acha, what is the importance of cell constant? Hey, mind this side, mind. Cell constant is what? I told na that one electrolyte we are taking and that electrode we are dipping into the solution. Conductometric titration. Remember, the electrode we have dipped na. So there we had two electrodes, 1 square centimeter area, and the gap is 1 centimeter. So that's why L by A was taken as unit 1. We have taken L by A equal to 1. This L by A parameter is called cell constant. It may not be always 1. In our case, it was 1. For simplicity, our makers, manufacturer, they are making it 1. But it can be others also. So that is the importance of the cell constant. Cell constant is a parameter L by A. SI unit for the specific conductance is SM inverse, means it is Siemens inverse. The unit is called Siemens. Molar conductance. This also I have discussed here. This also I have discussed already, isn't it? Lambda m I have used the symbol. Lambda m equal to kappa into 1000 by capital M. That is molar conductance. Equivalent conductance, lambda equal to kappa into 1000 by normality, and that was molarity. This one is normality. Now we can compare obviously lambda m by lambda eq. We can compare. So from these two equations, you will get molarity by normality, something like that. This plot also I have discussed already. This is the plot. Whatever I am discussing the board, you will find it here also. So this is for strong electrolyte, this is for weak electrolyte. Root C versus concentration is plotted. And normally here molar concentration is plotted. And at C tends to 0, the value we get here, that means the intercept of the, this is the intercept.
Sir, how it is possible?
How it is?
At the 0 point you get value.
No, interpolation. As interpolation, as I have drawn in the board. Interpolation. Dot. Acha, one thing. So theoretically we can make it, not practically. So we can make it dotted and it will touch. Now this intercept y equal to mx plus c, this is the c part. Y equal to mx plus c, na? This is the c part. So from this, what do you get? What is the c part here? Lambda 0. That lambda 0 is the c part here. Y equal to mx plus c, so c part is lambda 0. Now, this is the molar conductance, this is the equivalent conductance, this is the relationship. Molar conductance equal to valency factor or N factor into that equivalent conductance. This is equivalent conductance, this is molar conductance. That is the relationship. And in between there is a valency factor or N factor. Depending on electrolyte, if you have a univalent electrolyte, there is 1. If it is a bivalent electrolyte, there is 2. Give one example of bivalent electrolyte. Calcium chloride. Calcium chloride, bivalent electrolyte. Calcium chloride. Monovalent, sodium hydroxide. Sodium hydroxide, sodium chloride. Acha, Coldhouse's law, already I told you, this is the total conductance for the electrolytic conductance equal to the cationic conductance plus anionic conductance. Lambda A for anion, lambda C for cation. So cationic conductance plus anionic conductance giving you the total conductance of the electrolyte. This lambda at infinite dilution, that's why infinity symbol given. Infinite dilution, we can put 0 for 0 concentration. We can put infinity for infinite dilution. Same thing actually. You can take infinity symbol, you can use 0 symbol. If you use 0 symbol, you are signifying 0 concentration. And if you give infinity, that means infinite dilution. So that infinite dilution condition, the total conductance equal to anionic conductance plus cationic conductance. That is called Coldhouse's law. Now what is the importance of this law? Now think over. What do we do with this law? What do we do with this law? इसे करेंगे क्या? Right? That you must understand. Sometimes what happens, it is very difficult to get the conductance of suppose acetic acid, which is weak electrolyte. So practically what we do, we take the help of Coldhouse's law. We take sodium acetate. So sodium acetate and hydrochloric acid and sodium chloride. We take the three things: sodium acetate, hydrochloric acid, and sodium chloride. And then with the calculation we can find out the lambda 0 for acetic acid. We want to get the lambda 0 for acetic acid, for example. Based on this Conductance's law, there are some mathematics also. We can use this as just like a mathematical formula. We can use this. So we want to find out lambda 0 for acetic acid. By real experiment, it will be very difficult to do, because if you add more and more and more water, the conductance will initially increase, and after that practically you will find is if it is too diluted, you are not getting the result, not desired result. Okay, you are not getting conductance is, it will becoming like this, the conductance is more or less same. That happens. So how do you get it? Practically it will be difficult. So what we do, we take this value, we take this value, and we take and from that we can get this one. So that is Conductance's law. That is the application of Conductance's law. What do you do with the law? I told you, no? What do you do with the law? With the application of this law, we can find out which is not directly feasible. By doing experiment, you can get it. We are not getting it. Not getting the desirable result. Okay? Because if it is too diluted, practically very difficult to measure. So, with the help of this formula, we can easily find out. So, this is our conductometric titration that we have already done. So, I can go very fast because it is known to you. Conductivity cell, conductometric titration application. This is the way we are doing, right? Achha, do you remember why the color is changing? No, why? Phenolphthalein, but why it is happening, the color change? I told you already. In aqueous medium, if you add phenolphthalein, in acidic medium it is colorless, and alkali medium it is pink. Because in acidic medium you have phenolic rings. Phenolic rings, not pH, phenolic rings. You have structured phenolic rings. And in alkali medium it is quinone rings. Quinone ring. And quinones are colorful. Not quinol, quinone. Quinones are colorful. And acid medium it is colorless because it is phenolic ring. And alkali medium it is colorful because it is assuming the quinone rings. So that's why the color is changing. You need to understand why the color is changing. Not only that color is changing, why it is happening, you need to understand. Okay, so you read out afterwards. I don't have that much of patience, I cannot read for you. You read it. It is already there. Okay. So lot of things, details are there. Why so much of things I have written? Because this is replacing your books. If you read it thoroughly, then no need to read any book. Everything there. That's why I made it so much of informative. It's full of information. If you read it, no need of any book. Achha. Conductometric titration, this thing already have done. NaOH, HCl, NaCl, water. This actually we have done. What are the advantages of conductometric titration? Solution, if colorful already, this is one. This thing also I told you, that if the solution is already colorful, then you can take the help of instrumental method. And also another thing, you get the actual neutralization point, not the end point. End point means it is already alkaline, then only your color change you are observing. But neutralization point, that is one equivalent acid will neutralize one equivalent of alkali. These two will actually react with each other, and the neutralization point is the theoretical aspect. That is not practically found. And your end point titration, color change, that way if you do, that is called end point. So they are actually not exactly the same. So neutralization point if you want to achieve, then instrumental method is better. Lot of details there. Now next I'll show, yes, coming to the actual titrations, different types. Now I want to discuss the different types. One is acid-base titration, displacement, precipitation, redox. These all types of titration can be done by conductometric. But not by conductometric method. Here we are going to discuss about conductometric method only. All precipitation also can be under conductometric titration. Let me discuss one by one. First of all, acid base. Acid base you have done, so nothing to discuss much here. So you have got theory idea also. Because in the lab also I discussed in detail everything. So here you have taken HCl, NaOH and then reaction you are doing, and conductance is changing like this way. So initially the fall is very sharp, but the rise is not that high, slightly flattened. Okay. No, actually this graph I am not very happy. I could not get better graph from the internet. It is taken, na? So I cannot draw whatever I feel like. It will be like this. And another thing, here 2-3 reading you are supposed to get same. 2-3 reading you are supposed to get same. You are not doing mistake. Actually it is supposed to be same. 3 readings at least comes same. It should come. May not be. There may not be any difference at all. Some cases you will find there is no difference at all. 3 data same. That is called recurrence error. Why does it happen? Try to follow. Why does it happen? When you add more and more this alkali from the burette, dilution is there. Getting diluted. Okay. And at the same time, you are adding ion. Ion also. So ion is getting increased, and due to dilution it is decreased. So these two are balancing each other at that particular point. Why? Because the value is very low, and at the low value only this type of small factor will be very prominent. When it is highly concentrated solution, this small factor may not be so dominating. But if it is a very low concentration, low at the minimum value, there little bit of changes also will affect a lot. So two things are cancelling each other. One is the dilution, other one is the adding the ion. So concentration is increased as well as decreased, both are happening. At this point it is felt maximum. I can say it is felt maximum at this point. And that's why 3 readings more or less come in the same. So this particular point is called neutralization point or equivalence point. This is not the end point. Neutralization point or equivalence point. That you cannot get by only color changing titration. That you can get only by instrumental method. This is another one, strong acid weak base. This you have not done. You have done only strong acid strong base. Now you see here strong acid weak base. If you do, then you get the plot like this. Why? Because this ammonium hydroxide added here will not further dissociate and will not contribute towards conductance. It will not give OH minus accumulation. If you add NaOH more and more, then OH minus gets accumulated. After the equivalence point, if you add NaOH more, then OH minus is getting accumulated in the solution. Jama hocche. Collected. Getting added up and getting collected over there. Badhte ja raha hai, concentration is increasing. But here, ammonium hydroxide is not a strong electrolyte, it is a weak electrolyte. No, not saturation. NaOH, if you go on adding more and more NaOH, so you are actually adding more and more iron. But here, if you add ammonium hydroxide more, you are adding more molecules. Ionization is very little. Ammonium hydroxide ionization is little. No, because ammonium hydroxide is not that much ionized. Iron required, not concentration required, iron required. Sodium hydroxide has a lot of ions that is contributing towards conductance. Ammonium hydroxide is not contributing much into conductance because it is not ionized much. Non-ionized. It is a molecule. Ionization হচ্ছে না, ionization কম হয়. Sodium hydroxide is highly ionic. It is getting ionized. But ionized means from the beginning it is ionized. Because
So it is present as a molecule.
it is present as a molecule, so ions are very little.
It can't break into the
Not much. Maybe 15%, 20%. That's why here it is not enhancing the conductance. Conductance বাড়ছে না. Next one. It is strong acid, weak base. No, weak acid, strong base. Strong acid, weak base already you have done. Weak acid, strong base. So for weak acid, strong base, the plot will be like this. I can explain. Hey, listen. So here what is happening? Initial there is a very little fall. Because some amount, whatever weak acid, some amount of H plus is at the beginning there. That will be removed by adding some alkali. This H plus, whatever H plus was there here, is removed. That's why conductance is falling. Whatever amount of H plus present at the beginning, that is removed. That's why conductance is falling in little. See, there is a little fall.
removed by who?
Removed by OH minus, H plus plus OH minus equal to H2, H plus plus OH minus equal to H2. That reaction taking place, that's why H plus is removed and conductance is falling at the beginning. Just at the beginning. After that is rising because here sodium acetate is formed. You are adding more and more sodium hydroxide. So sodium acetate is formed and sodium acetate is also a salt. Weak acid, strong base, but salt has got certain contribution towards conductance. Salt is ionized always. Sodium acetate is ionized. That's why it is contributing towards conductance. So conductance is increasing. More and more salt, so more and more conductance. But slight increase. Why slight increase? Because these are very bulky salt, so their movement is slow. Because not only the number, but the size also matters. Na? Already we have discussed. So this is slow. Ionic mobility is low ionic mobility. Okay.
But sir, why it is
ওই পরে কথা বলবে নালে পরে কিন্তু বুঝতে পারবে না শুনে নাও.
why it is from ionic part? I mean,
No, salt is always ionized. Maximum salt is ionized. Salt is maximum ionized. Little bit of non-ionized. Because these are crystal lattice they are forming, na? So then unless forms the ion, they cannot form lattice. So practically all salts are crystalline, na? Crystalline means there is ion. Otherwise, how can you get the lattice? They are ionized. From the beginning, they are ionized. No question of ionization. Salt is already ionized. So sodium acetate is ionized, and in aqueous solution, obviously it is ionized. So it is giving more and more conductance. After nucleation in OH is just like the earlier. It is rising because of accumulation of OH minus. So this plot is clear or not?
sir, this part I can't understand.
Which one?
Accumulation of OH, sir.
वो accumulation में जमा हो जाना कलेक्शन हो जाना. Accumulation means agglomeration. एक जगह पे जमा हो जाना.
तो वो बढ़ता क्यों?
तो बढ़ेगा ना. OH माइनस बढ़ रहा है ना. OH माइनस का कॉन्टैक्टेंस नहीं है.
हाँ,
वैल्यू देखा है ना कितना हाई वैल्यू है ना, तो कॉन्टैक्टेंस तो बढ़ेगा.
जमा हो रहा है बोले तो क्यों?
जमा होगा तो जमा नहीं कॉन्सेंट्रेशन बढ़ रहा है ना उसका. OH माइनस का कॉन्सेंट्रेशन तो बढ़ रहा है ना.
But mobility
नहीं मैं एक जगह पे उसका क्लस्टर नहीं कर रहा हूँ,
तो
मिक्स कर रहा हूँ ना. सो कॉन्सेंट्रेशन ऑफ OH माइनस ओवरऑल इज इंक्रीजिंग.
why it is increasing?
You are adding, that's why. You are adding from the burette. Na?
Anyways, na sir.
You are adding anyways, na?
हाँ, तो it form
It is not forming anything. OH minus is already there. When you are adding anyways, actually you are adding Na plus plus OH minus. So OH minus is already there. So more and more OH minus is enhancing the conductance.
अच्छा, तो जब H plus ion finish हो रहा है
Finish.
तो वो
Yes, after H plus is already over. Now there is no H plus. Or very minimum H plus. And then in that case, if you add more and more NaOH, so OH minus is getting enhanced, concentration is increasing.
so it increases the
So increases the conductance. Hey, listen. So at the beginning, acetic acid also has got certain amount of H plus that is removed by adding NaOH. So their H plus has a very high conductance. If it is removed, conductance must fall at the beginning. So it is falling. There is a small kink. This is called a kink. So there is a small kink, and after that there is a rise. And after equivalence point, there is a further rise because of again accumulation of NaOH. Accumulation means after utilization, the NaOH has got no utilization, so it is increasing the concentration only. In this case, just a combination of these two things. One is this is weak acid and weak base. So the plot is also like a combination of other two.
Accumulation is why not here, sir?
Hmm?
Accumulation is not why?
Accumulation. Oh, ammonium hydroxide is not ionized. Accumulation is there, but not
Can't
ionized.
break into ion.
No, less, very little, 10-15%, 20%, not more than that. And if the concentration is increasing, rising more and more, ionization is decreasing. Higher concentration. দুটো slope তো আলাদা, two different slope. This is parallel to x-axis. See, this is parallel to x-axis, but this is rising upward. So there is intersecting point. मिलेगा? Next is displacement reaction. Displacement reaction is this: ammonium chloride plus NaOH. You are getting ammonium hydroxide plus NaCl. So how will be the plot? Tell me. Ammonium chloride. So this ammonium hydroxide, low conductance. So conductivity will fall. Na? This is ammonium chloride, high conductance. Sodium hydroxide you are adding. So conductance at the beginning is high. More and more ammonium hydroxide is formed, which is less ionized. So it will become, so continuously there will fall at the beginning. After the nucleation, then there will be more or less parallel to x-axis. This is a combination of so many. All of them are combined together. If you take two different acid mixture, you get a combination of plot. Acidic acid HCl mixture. You do the titration with NaOH. There will be first fall, then like this, then like this. This. Okay. Combination of HCl and
सर वो पिछले वाले केस में पहला जो टिप आया था ना
king, the small king.
दिखाया था ना तो आएगा सर
दिखेगा नहीं, because mixture है ना, वो दिखेगा नहीं.
बट सर इसमें भी तो कुछ Na प्लस और Cl माइनस होगा ना पहले वाला
This is a combination you get for strong acid and weak acid mixture. In which you are adding, and this is the conductance. You get first fall, there is slight rise, there is sharp rise. এটা হচ্ছে HCl plus acetic acid and titrated with NaOH. So the initial fall will be due to HCl reaction, first HCl reaction, then acetic acid reaction, and then accumulation of NaOH. What was your question now? কিছু একটা বলছিলে।
हाँ सर ये टिपटा वो
King, the small king. ওইটা না?
हाँ सर
No, that will not. You cannot observe here because you have a very strong acid, and in the presence of that strong acid, the weak one will be suppressed. जब बड़ा वाला बात कर रहा है तो छोटा वाला का बात नहीं करना चाहिए।
And for the
तो
previous
HCl है तो उसके सामने उसका औकात क्या है?
for the previous case sir
जब HCl है उसके सामने एसिडिक एसिड का क्या औकात है कि नहीं? बड़ा वाला चल रहा है उसके साथ छोटा वो सप्रेस हो जाएगा, उसका अंदर दब जाएगा वो।
और पहले वाला इसमें NaOH और
सेपरेटली कर रहा हूँ ना,
NaCl था
हाँ?
इसमें NaOH और NaCl था
ये वाला
हाँ सर
NH4Cl plus
Cl
Na।
माइनस रहेगा ना
सोचो दिस अमोनियम क्लोराइड इज ए comparatively good conductance, not very high but good, plus NaOH you are adding from burette. So conductance is falling because ammonium hydroxide is producing, so conductance is falling. There is a plot like this. After that, after the nucleation, you are accumulating more and more NaOH, so there will be increase. So that means this and this, just like our first strong acid strong base nucleation, it will be more or less like that. Achha, this is precipitation. KCl plus AgNO3. Now AgNO3 you are taking the burette and KCl you have taken into picar or conical. Now AgNO3 you are doing conductivity titration, so it should be picar not conical because electrode immerse na. So in the beaker you take KCl and add AgNO3 from the burette. KCl you are taking into beaker and AgNO3 in the burette. Now after that what you get? initially conductance will, what will happen? KNO3 will form and AgCl is getting precipitated. That means some loss of ion is there. Loss of ion. Acha, initially, okay, just think. This is in the burette. Don't consider this because this is not there into your mixture. It is in the burette. So what you have as a mixture? Only KCl. In the beaker, what do you have? Only KCl. Okay. Now you are adding more and more AgNO3. So what is formed? KNO3. KNO3 and KCl, they are almost same conductance. KNO3 and KCl, KK common, Cl minus and NO3 minus, not much of difference. So क्या होगा? Plot will be parallel. After that, accumulation of AgNO3 rise. So parallel, then rise. This, then this. Got the plot? ট্যাপ ওয়াটারে তো করেছো তোমরা, কিন্তু কন্ট্যাক্টেন্স যদি করো কিছু টেপ পাবে না। তো ট্যাপ ওয়াটারে আবার কি কন্ট্যাক্টেন্সই পাবে না, সেই জন্য কেসিএল নেওয়া হচ্ছে। ওখানে হচ্ছে প্রেসিপিটেশন, তুমি দেখতে পাবে না, বুঝতে পারবে।
লেখা ছিল ক্লিয়ার স্টেটমেন্ট যে দ্য কন্ডাক্ট্যান্স রিমেইন সেম।
এই তো হচ্ছে, এই যে এইরকম হবে প্লট, প্লটটা এরকম, প্লট উইল বি লাইক দিস। Okay, so I stop it here because time is up for this